Okay, today we have a fully packed agenda with lots of insights on our more technical and scientific developments, but also with poster sessions, demo sessions, and towards the end of the evening we will have a reception at Bellevue, but we will come back on this later. So to avoid that we delay the agenda a little bit too much, I would now go to the first session of the morning, which is from observations to essential climate variables.
Good morning, everyone. Thank you for coming so early. So I will co-chair this session with Joachim. And if we go to the first presentation on this. So yesterday we had a reminder of this address that had been made by UN Secretary General. And what's interesting about this is that he talks about tipping points, he talks about playing Russian roulette, he talks about a lot of vocabulary that is talking to many people about what is happening with the climate. But more interestingly, for us, of course, he starts with a reference to C3S. And this explicit reference to C3S is just at the bottom. It's just at the beginning, like a blip for people who may not read the rest. And in fact, if you look at the quotes in the media, they're not quoting this particular bit, they're quoting the rest, the Russian roulette and all of that. But it means that this is all based on a lot of information. And so this is the visible part of the iceberg of the climate information. It arrives here at that level, bubbles up, people don't see the rest. And the rest, we're going to talk about it now. How do we get there? So how do we get there? Well, it's a bit like going to the moon, in the sense that we need a big rocket with many parts. And the Saturn V rocket had 3 million parts. Each part was quality controlled and checked by an array of industry, university and best people who could do the best of their job in their area. So here it's very similar. We rely on a lot of parts, and all those parts are pieces of information that are coming from observations, from models, from science. So what we'll do is we'll have first a scene setting talk by Professor Thorne. He will talk about this blueprint. How do we build this rocket? How do we decompose the problem into smaller parts? And those smaller parts, actually at some high level, are called the ECVs. So we'll have an explanation on that. For those of you who are familiar with ECVs, you will still get a lot of interesting information in this talk because Professor Thorne will tell us about the evolution of the ECV decompositions. What is being thought about? How will it look like in the future? Then we'll have 3 examples of ECVs, how to make ECV products: in situ, space, and reanalysis. So I will not take any more time. If you have questions, please keep them for the end of the session. At the end, we'll have a little panel discussion. So now welcome Professor Thorne. Thank you.
Okay, thank you very much. Hopefully my presentation will come up in a second. Okay, so I'm going to talk about an ongoing process that we have in the Global Climate Observing System on ECV rationalization. And we've had essential climate variables, that's what ECV stands for 20 years. And they've grown and developed over that time, and we now have a grand total of 55 essential climate variables. Now that starts to break the tenuousness of the word essential. If you say 55 things are essential to observe. But are we missing anything? Is the current grouping the best possible one? Is there enough transparency and coherence in the process? Are the concepts used consistently across GCOS and across science? So, if you like, GCOS ECVs are having a midlife crisis. So those were questions that when C3S graciously hosted us for a joint panel meeting, and thank you C3S for hosting GCOS for that joint panel meeting last year, led to the establishment of a GCOS ECV rationalization task team. And this is the task team in all its glory. Carlo, the beehive, was back and to the right a bit from this picture, the way you're looking at it now. We have 3 members per GCOS panel. So GCOS has long been split into 3 panels, one for the atmosphere, one for the ocean, one for terrestrial. We have 2 external experts, and thank you, Carlo, for being one of them. We've had online meetings, and we had a meeting in Potsdam just last month. And what we're thinking about is how do we improve the governance of the process for the adoption? What are the definitions of both ECVs and ECV quantities? So ECVs are the things we want to observe. ECV quantities are the things that are observable about those things. So we want to observe sea ice, but saying you want to observe sea ice is not particularly good, particularly tractable. What do you want to actually observe about the sea ice? You want to observe things like its extent or its concentration or other things. And we now have put on our brave boy and brave girl pants and come up with a proposal of ECVs and ECV quantities that we are about to go out into the brave world with. And this is very important. What you see here is not the end point, it is the start point. There will now be a 2-year-long journey of both one-to-one with key stakeholders and then public engagement and an opportunity for everyone to come forth and say how bad we are and how stupid we are. And trust me, I'm stupid, I know that. So nothing is locked in at this point. So the definitions, we've tried to go through the definitions and increase the relevance and importance of the ECV quantities. And that's because well-meaning, and many of the people in this room are behind that, well-meaningly, people have gone, we need to observe all the ECVs, and they've gone, we've got 20 ECVs, we've got 20 gold coins, here are 20 gold coins, go and look at your ECVs, folks. The trouble is some of the ECVs are massive things that are measuring many aspects of the climate system of that particular essential climate variable. They need a lot more resource to be observed than some of the others. So we are trying to bring up ECV quantities, the things that are observable, to the same level as the ECVs themselves, and to highlight that some ECVs might have 2 or 3 quantities, others might have 10. And that's important when we're making decisions as to what to support. We also have come up with a much more robust adoption process that will involve a proposal from the community, review within GCOS across the panels, and eventually by the steering committee. So no longer will it be a nod through on the steering committee in the last 10 minutes of the last day. It will be a rigorous process. If you want to proceed to propose an ECV, there will be a rigorous process. So what are the changes we've done? We've done some regrouping and reordering. Some ECVs have become ECV quantities, this should say, not products. So we have collapsed some of the 55 current essential climate variables into families of a new ECV. We have removed a couple of ECVs with the name anthropogenic in them. This is because anthropogenic greenhouse gas fluxes, for example, we have been told repeatedly is not an observable. It's the greenhouse gas fluxes themselves that are observable. We have added some ECV quantities, and we have changed some terminology for consistency. Maybe this will go forwards. Okay, so I don't expect you to read this because it is unreadable. But on the left in each case is the original set of ECVs, and then on the right is the subset of ECVs, and it's by panel, so atmosphere, ocean, terrestrial. There will be, if you have questions afterwards, and we have the 2 minutes, so we'll go through with the larger set. But I'll go through very quickly with some of the atmosphere, which is the panel I chair. And here we've collapsed down the number of ECVs considerably. We've removed the distinction between surface and upper air. Temperature is temperature. It doesn't matter whether it's 1.5 meters, 5 meters, 10 meters, or 10 hectopascals. It's still temperature. And we also have things like precipitation is staying, but we have a lot of rationalization. We hope this makes more sense within and across panels. So, next steps. We're going to reach out to key stakeholders, including many of the organizations who are represented in this room, for one-to-one engagements. We will come to you, we will ask your opinion of the whole package, the definitions, the governance, and the ECVs proposed. Next year, at the start of it, we'll revise as necessary, depending upon the feedback we've received. Then we'll go to public review, and then at the end of next year, we'll finalize, we'll write it up, we'll include in the GCOS status report and the implementation plan, which will be the official switchover. And remember, when you're looking at this and looking at the slides that will follow in a minute, nothing is final until everything is final. Okay, so thank you very much. The B's just for you, Carlo. And I will now hit forward, and it will hopefully animate. So these are the new ECVs. Thank you very much.
Thank you very much. If there are no immediate questions of clarification, are there any in the room? No, I don't see any.
It will take about a minute and a half to cycle.
It sinks, yeah, okay.
I would like cycling, so it's working.
Thank you. Thank you for this overview. So indeed, this overview of the blueprint is showing us how many parts need to be looked at. And this decomposition of 55 is actually interesting. And I'm still using the word ECV products, so you will have to tell me. If you want to ask questions online, I remind you there is a Slido hashtag C3SGA, all uppercase. So please online, feel free to ask questions and we'll look at that in the end. So, okay. All right, so now we'll move on to the next presentation. Professor Fabio Madonna from University of Salerno. He will talk to us about the in situ aspects of how to make ECV products. Quantity.
Okay, thank you. Good morning, everyone. Well, we are going back. I think we need to switch the presentation, sorry. No, doesn't work.
Something's gone horribly wrong.
Well, okay, thank you so much. So, with the activities made during the first and the current phase of Copernicus for the in situ datasets, we have been able to publish in the CDS or to submit, so still under evaluation, several datasets which are from reference and baseline networks covering nearly all the ECVs in the atmospheric domain, which you can see listed on the right side from the list provided by GCOS and also shown in the slides provided by Peter. So at the moment, the variable which is covered and publicly available with several datasets in CDS is only ozone. But very soon, several other datasets will be available covering aerosols, CO, CO2, CH4, formaldehyde, NO2, and this will be from both reference and baseline networks. In this presentation, I will be presenting a few examples of in situ datasets for a few ECVs, mainly this will be for NO2, aerosols, and ozone. Let's start with, well, no, please, go ahead. Okay, with ozone, okay. We provided several datasets covering most of the measurements techniques available from the ground, from reference and baseline networks. You can see on the left side a few examples for the techniques historically, but also more recently used for measuring total column ozone, and on the right side, instead for measuring the concentration along the vertical profiles. As I said, most of these datasets are already available. More will come. Please, next slide. I'm not sure why, but it's fine. So given that we are in Brussels, let's start showing examples of one of the longest data record available within the ozone profiling datasets. This is the time series collected at Uccle Station here since 1970, and it's a really huge data record, and there are many more available. Please, next slide. The fact that we have so many different data sets covering the ozone measurements along the vertical profiles is also amazing because we can exploit their synergy, because different techniques can cover different ranges. This is an example coming from an index station in the southern hemisphere at Lauder in New Zealand. Measurements are provided through the ozone soundings from 0 to 35 kilometers on average. with the LiDAR from about 7 to 50 kilometers, with the FTIR from 0 to 50 kilometers, and then with the microwave radiometer from 20 to 70 kilometers. Putting all of them together, as shown by the vertical bars on the left side, we are able to characterize the concentration, the vertical profile of the ozone concentration from the ground up to 70 kilometers. Please, next slide. A key element we provide from reference network is the uncertainty. Uncertainty is the only way we have to provide confidence in our findings, to improve homogenization and consistency of our data records, to validate quantitatively other data sets, which means models, reanalysis, or satellite, and also to support decision making. This is an example from a station, again in the southern hemisphere, from Shadowts. You can see two panels. On the right panel with the red line, you see the estimation along the vertical profiles of an ozone sounding of the uncertainty in terms of ozone partial pressure. On the left side, you see all the work behind, the quantification of all the instrumental environmental effects producing an uncertainty, which means the range within we know that our best estimate is varying. So, having so many data sets available for ozone, we also thought to provide some unified data sets. So we decided to put together the data from different networks. You see listed all of them on this slide. And we provided other two additional data sets in support of the C3S users. One is unifying about 160 Dobson sites, and we have also another one for Brewer along, let's say, worldwide. And on the right side, you see what we made instead, putting together all the ozone sounding stations from three different initiatives, and Shadowts and Woodsea. This is offered to the C3S user to avoid to download single data sets, to have a very, let's say, a complete overview of the data available, and also these data sets have been designed to remove duplicates and report flagging on the data quality and on, let's say, also different, let's say, characteristics of the data sets. For nitrogen dioxide, we have two data sets mainly, which comes from the same measurement techniques, the max DOAS, from PGN and from NDAC. These data are already used for the validation of two main products from Tropomi instruments on board of Sentinel-5P. This example is showing the validation for the stratospheric NO2 concentration. And you can see what's the value of having these in situ measurements at several sites around the world, because it's not said that an algorithm from satellite is providing data with a clear bias and with a clear spread around the bias. So this is very different at different latitudes. Please, next slide. And here we report in form of box and whisker plots the bias and the spread for the difference between the NO2 concentration in the troposphere from Tropomi and from the in situ sites. And again, you can see that the in situ can really characterize the performance of the satellite retrieval algorithm. Finally, for the aerosols, we provided, and this is still under evaluation by C3S, a climatological dataset providing made by aerosol optical properties, extinction and backscatter coefficient, and also their ratio, which we will see soon, it's extremely useful, and their wavelength dependence. This is characterized in form of an example of a measurement at Potenza station in South Italy on the left side. And this is translated for the C3S user in a seasonal or monthly. In this case, the example is showing a seasonal average, but we have also monthly averages. This is a time aggregated product offered to the C3S users to facilitate climate studies and application. We know that the overall effect of aerosol on the radiative budget is to be a cooler. But it's also true that the let's say, the uncertainty we have on quantifying this effect is still quite large. And the key element is to identify the aerosol types, because only in this way we can really address the radiative effect. This can be properly done looking at a few intensive properties we provide in this data set. LiDAR ratio, the extinction to base scatter ratio, which is really depending on the aerosol refractive index, so the aerosol nature. In this example, we see the statistics provided in the data set showing, for example, that ZVN in a few seasons, LiDAR ratio in the UV region of the spectrum with a value of about 40 steradians, we have mineral dust. But if we have instead something like 60 steradians on average, we are looking at biomass burning, while if we have even higher values, up to 70, 80 steradians, we have pollution. So that's a very useful information for the C3S users. And in addition, in the dataset, we have also other properties about the depolarization power of the particles, which, if put together, if used in synergy with this one, can provide a much more efficient typing of the aerosols. So I conclude just saying that, in summary, C3S will offer very soon several data sets covering many different atmospheric ACVs from reference and baseline networks available worldwide. Thank you.
Thank you very much, Fabio. Are there any questions from the room for clarification? Yes, one?
Sorry, thank you for the talk. Very, very good. On the last slide, the plot refers to an average over a number of years. So the accumulation, the last histogram was over a windows of 20 years. Or
yes, I mentioned the period in one of the former slides. It's since 2000 to, at the moment, 2019, but the next update will be up to the present time.
Thank you.
Thank you for this question. So let's move on now. So I invite Lothar Schuler from EUMETSAT to talk to us about how EUMETSAT contribute to observing those ECVs. Thank you.
Thank you. Microphone is on. Can you hear me? Yes. So good morning. Before I start, I'd like to show you something. I just yesterday cleaned up my desk and I found this little gadget and piece. It's what we call in German a Wackelbild, a shaky image, where you can see several images depending on the viewing angle. And I had this done some years ago when we really discussed our data records, satellite data records, long enough to compare it with the current data and looking to it in terms of anomalies. And that was very exciting. So I had this done combining a CMSAF data record on a sunshine duration and soil moisture from the scatterometer. And you can see it, let's say, compare it in an analog way, works without battery. Very good. So in this presentation, I would like to show you some aspects on how we arrived to it. Yeah, it works. So I'm with EUMETSAT, so the satellite organization for the meteorological satellites in Europe, and we have a SAF network, and that is, I'd say, a network where we include the expertise in our member states and grouping that, and we have 8 different SAFs looking to some topics, and each SAF is a network itself, and they are providing operational products based on satellite data or related to satellite data on specific topics, including climate monitoring, but also other aspects, as you will see. And let's say the main feature of it, like more or less everything that we do at EUMETSAT, is to do it in an operational way. So what does it mean also for the SAF and the products is it has to do a lot of with continuity, so products continuously provided to its users, but also product improvement, quality monitoring, user services, but also documentation and validation of these products. So this is some key aspects on it. And there are several satellite products related to ECV quantities that can be found in a climate data store of C3S, and just want to show them to you. There is some radio occultation products, tropospheric humidity, the profiles Peter knows very well, I think, and then several products from the climate monitoring staff related to water vapor, to clouds, and also was mentioned sea ice this morning already. So the OC staff are the staff responsible for these types of observation, from sea ice edge, sea ice concentration, and also water vapor from the CM staff. So several products are available through the climate data store, but and which we are quite proud of, that we can contribute with the SAF network to it, and even more that these data are used to analyze the state of the climate, like in the recently published European State of Climate report of C3S, looking to the anomalies, again here, sunshine, duration, and sea ice as an example. So we are really a proud contributor to this exercise. So I would like to give you some insights on the concepts, why these satellites can be used in that way, and what it means for satellite or processing the data. So, of course, anomaly detection is somehow to relate the current information of the current or just the past month to a longer term observations and statistics. So what are the ingredients that are necessary is, of course, the data of the last month or the current week or whatever, but to put this in relation to a long-term data record. And now we can have, with our satellite system, also covering decades of observations. But the point is, it's not enough, but it has to be consistent. So the current data needs to be consistent in terms of processing and even ingredients and methodologies to the long-term data record. So the consistency is very important, or is a prerequisite of it. So, and this allows us to have a system that is regularly updating month by month, or maybe sometimes in even shorter time period, these longer-term data records, and having every month the possibility to look to anomalies, or feeding it into a system that generates these anomalies in combination. And another aspect, continuity, I try to explain it here, is not only having the system climate data records, and this is how we call it, interim climate data records, having it set up once, but also to use the expertise in the sustained structures to even further develop, further improve the system, incorporating the new science and maybe new technologies, to have from time to time an update, a new version of the whole system, a climate data record, and at the same time also updating the continuous generation of the ICDR, interim climate data records, as we call it. So this is our concept that we developed over the years, also in international discussions, and I think this is the prerequisite. Another aspect I would like to highlight is how to combine different generations of satellites. This is quite a challenge. And for example, Meteosat. We have now operational the second generation of Meteosat. We have had the first generation of Meteosat, and also the third generation is already in space and currently in the commissioning phase. And this is an example of a recently released data record from the CM staff on land surface temperature. So covering almost 40 years. So that's pretty amazing. I think some of you are younger than this data record here. And this has been done in using to do a consistent processing of and combination of the first generation and the second generation of the data to reach this long-term data record, and having, for example, here these monthly diurnal cycles of the land surface temperature. And the aspect here is, in order to do that, to ensure the consistency, you have to compromise some things. You have to make a decision, and you have to, in this case, to sacrifice the best possible result from the newer generation in order to achieve the consistency. So to discard some of the new channels that are only available in the new system. Yeah? And that also means that it may be a bit confusing, that depending on what you are emphasizing on, what you need, there you can find various different ECVs, quantities, or products with different temporal coverage, resolutions, and accuracy. And that's not a question of better or worse or right or wrong, but it's just to see what the aspect is, to have a longer data record with some compromises on resolution and accuracy, or a shorter data record, for example, just based on Meteosat second generation with better characteristics. So for me, this also means that we have to be very clear in the communication and the documentation of the product to understand really what the purpose is, and also discussing with the users to clearly understand what is required for which applications. Let me come to the conclusion. So the EUMETSAT satellite application facilities provide in a sustained way satellite data records for various purposes, and feeding also the C3S. We reach with Meteosat, for example, we reach now almost 40 years of temporal coverage. We have this concept of having consistent extension of the data records, which we called ICDR, which is the prerequisite of reliable monitoring of the anomalies. And the SAF network is a partner of C3S in many aspects, in providing not only the products, but I also have to mention the providing also the ingredients for the reanalysis, the more basic products, together with our colleagues from the Secretariat. Yeah? I would also not miss the opportunity to mention there is an excellent coordination relationship between the services, the SAF network and the C3S, and I think that leads also to a privileged access, not only to the data, but also in the understanding of the requirements that I mentioned before. A quick outlook to the future. Of course, in the SAF network, we will see, and we will also discuss an increase of the portfolio, so adding new ECV quantities, also adding new ICDRs to data records where we don't have an ICDR yet. We're also looking to more explicitly addressing these anomaly and normal information as operational products. And I think in this context is important to focus even more on consistency. So also the different products and the different quantities and the different sensors, the continuation, and the aspect that I mentioned also to prepare to include the new generation of satellite systems in order to continue a certain legacy in a useful way. That's it from my side. Thank you.
Thank you very much. I think we will take your words of consistency and keep those ones for the panel discussion at the end. I now invite Deputy Director of Research at ECMWF, Stephen English, to present to us aspects on reanalysis. Thank you.
The green one goes forward. The green one goes forward. Okay, thank you very much, and it's a great pleasure to be here at the C3S General Assembly for the first time for me personally, and I just start by thanking Patricia Durrani for her help putting this together. Now, I'm from ECMWF, but I'm not part of C3S. I see, a few minutes ago we heard Peter Fawn saying how many of these ECVs there are, and I see the huge amount of work that my C3S colleagues at ECMWF have to do supporting large numbers of ECVs. So the question I always ask, if I can make this go forward. Okay, yeah. Why is this all independent? Why is reanalysis in one world and ECVs in a separate world? And it seems never the two can talk to each other. Could some ECVs be taken directly from reanalysis? So they said, well, why don't you come yourself to the General Assembly and ask that question? So that's why I'm here. Okay, now just a bit of context. I come from the weather prediction world, numerical weather prediction. And if you look at the performance of numerical weather prediction over the last 40 years or so, you see it's getting better. The higher the numbers here, the better. These are just different forecast ranges from 10 days up to 3 days. And the difference between the two lines is northern hemisphere and southern hemisphere. And what you see is something quite dramatic happen between, if you look before the sort of 1990s and into the 1990s and afterwards, you see those two lines coming together. And what that happened was because within the data assimilation world and the NWP world, we started to understand better the characteristics of some of the satellite products we were assimilating and move towards using level 1 satellite data more directly, because we started to understand how some of the information you had to use when you were creating satellite data products was causing problems in the data assimilation and the forecast. And this caused a dramatic improvement in areas which were not well observed by in situ areas. So that's why the southern hemisphere and the northern hemisphere comes together here. So just keep that in mind during the rest of the talk. The basic problem when you're thinking about the spaceborne observations is that most satellite data inversions are what we call mathematically ill-posed problems. That means there isn't actually enough information in the observations to come up with a unique estimate of the geophysical space that we're actually interested in. You have to bring in some other information to be able to create the analysis of the quantities you're actually interested in from the satellite data. So what can you use? Well, sometimes you can use a synergistic approach with other observations, and that's great. If you can bring in independent observation information and that solves this ill-posedness, that's really, really good. Quite often, though, we see products which actually use a climatology, either implicitly or explicitly. And for example, everybody talks about machine learning these days. If you use machine learning to generate a satellite data product, then you've got an implicit assumption about a climatology from the training data for that machine learning algorithm. So it's used a lot, but it has disadvantages. And obviously, if you're trying to create a climate product, you don't really want to constrain that with some other climatology. You want it to be an observed ECV. And equally, you could use a model, but that's undesirable because we want these to be observations. Now, I've heard it used several times. Well, reanalysis is no good then because it uses a model. Well, I don't think that's, in some ways that's true, but it's not really relevant, I don't think, to this question, because what we're doing with reanalysis is that we're assimilating all the observations from the entire global observing system simultaneously to create analysis. So part of this ill-posedness is solved by just bringing in all the observations, but even that's not enough. But you're also projecting forward in time recent observations. Now that projection forward in time uses a model, but it's based on recent observations. And if you've got a mature model without very large model errors, then the actual contribution of the model error to the projection forward in time is very, very small. So bringing in, to put some jargon slides in, X is what we're interested in, and A is other stuff that we need to analyze it. All this is taken forward in time. Then you solve the ill-posed problem. So what reanalysis is really an observation-based product. But it's using the observations now, it's using all the observations now, and it's using information projected forward from the recent past. And that's why reanalysis is really very good at ingesting many types of satellite observations. And as long as the operators to do this projection forward in time and the data assimilation system are mature, and we don't have large dominant model biases and model errors, then reanalysis is a really good system for this. So when we look at what we're now doing with NWP, we focused on the atmosphere for a long time. Now we're moving towards an Earth system approach where we're trying to apply the same sort of approach to sea ice, ocean, waves, land. Now here we don't have the same maturity in all these systems. We've got very high maturity in the atmosphere, less maturity in the other systems, but it's changing. So we're evolving to a system where maybe already we can think about the atmosphere for some of these ECVs directly from reanalysis. But for some of these other components, maybe that will come in the next few years. So we should be really open, and what I'm coming here and asking for is a really open question and a really open discussion about what can really be taken from ECVs, what can really be taken from reanalysis for ECVs. So I just looked at some examples. I'm not going to have all the detail you saw in those earlier talks, but I just thought, here's one that's definitely not appropriate for reanalysis, glaciers. So it's primarily from high-resolution imagery data. The inversion problem is rather well posed compared to many others. Models are not mature and have a high uncertainty, and data assimilation isn't really active here. There'll be many ECVs like this, where clearly reanalysis is not an option, even if this was part of a reanalysis system. But we can look at others, and I pick here upper air and integrated water vapor, where the information is primarily derived from regencies. So we're into a very, very ill-posed problem mathematically, also a nonlinear problem. And in the numerical weather prediction world, we learned a very harsh lesson in the 1980s and 1990s about the danger of bringing in prior information to solve the ill-posed problem, and then not really properly taking account of that in the way we then use the products. So everything here is ticking the right boxes. The operators are mature and accurate. The data assimilation systems are very mature and sophisticated. And also the reanalysis method ensures physical consistency between variables. So I think for these sort of variables, especially atmospheric variables, reanalysis, we should definitely be having a conversation here. I mean, I'm not listing all the ECVs here, but I just thought you could start to categorize some which are probably always going to be best as independent ECVs. Glaciers, groundwater lakes, you can see some of the things I put there. Some I put at the bottom where I think we should already be having a conversation now. I think the systems are mature, and I don't really understand why we wouldn't take ECVs from reanalysis for some of these atmospheric products. And there are some where there's a direction of travel, where I think this is evolving, it's getting close to a level of maturity where we should be having a conversation. So just to summarize, my question to you as a community, C3S community, is could some ECVs be taken directly from reanalysis? My opinion, and of course I'm more than happy to have a discussion, is that for some this is probably already a good option. In the coming years I think it could be the case for many more, and there are some where it's unlikely ever to be possible. But if we can bring these two worlds together, reanalysis and ECVs, I think there are real benefits. There's some fantastic expertise in the community about generating these ECVs. We can bring that in, help that support the reanalysis effort if we think that's what we're doing. So it's not that we're not valuing the expertise. We want to bring that expertise in and bring it all together so we've got one joined up effort. And also we can also focus more our effort and time and energy on those parameters which absolutely have to be independent of the reanalysis process. So the whole thing becomes a really joined up approach. So that's my challenge to you, the C3S community, my question to you, and I'm very glad to be here and engage in a conversation about this. Thank you.
Very much. Thank you very much. So any clarifying questions, or I think we're going to jump to the discussion now. So we're going to have a little panel organized. I will ask you to please stand up here now, do we? Move up. And Joachim will run this session.
Oh, we get to sit. Okay, thank you very much.
In the meantime, just remember that you can send your questions through Slido using the hashtag C3SGA. So apart from the questions that come now from the audience. So okay, so we'll have about 10 minutes, I think. Well, this is gone. Sorry, the Slido thing is gone. So, we'll have about 10 minutes. So please put your questions, and let's start on the back. Anka, I think it is. Anka? Yeah. No.
Thank you. It's going to be a simple and possibly naive question, and it's to Steve primarily. Does your conclusion as to which ECVs could come straight from reanalysis depend on reanalysis? You reminded me that we talk reanalysis here and we mean European reanalysis, we mean ERA, ECMWF reanalysis. If you were to look at other reanalysis, would the conclusion about which can provide ECVs as well as or better than observations alone be the same?
Well, I wouldn't claim to be an expert in all the reanalysis systems to be able to give a really good answer, but for me the criterion is simple. If it's a very ill-posed inversion problem, so I'm primarily here talking about satellite products, if it's very nonlinear, and if you've got a mature systems, as I described for the atmospheric component in ERA 5, then for me it seems a no-brainer that you would take those ECVs from reanalysis because it's an optimal way of ingesting that satellite data. It's an optimal way of solving that problem purely based on the observation input. When you're talking about other parameters and other reanalysis, I'm not a reanalysis expert, so maybe others can answer that question better than I can.
I can come in and just say, of course, from the IPCC perspective, whereas the CLA in the observations chapter, we did use reanalysis for a broad range of ECVs. We might not have packaged them in C3S in that way, but I would just caution that it's not as pessimistic, perhaps, as Steve is making out, in that the reanalyses were used in IPCC, ERA 5 in particular, but also a range of other reanalyses precisely for the ECVs, that's the type of ECVs that Steve mentioned.
Yeah, hi, my name is Daan Hubert. I work at Bira, a few kilometers away. I lead the ozone CCI project of ESA and was also involved in the recent ozone assessments by WMO. So I've been directly involved in the problem of assessing compliance of satellite data sets with GCOS requirements. And my question is to Fabio, perhaps to Peter as well. I'm really concerned as being part of a validation team where ground-based data are really essential. The ground-based community is really suffering to get data running for the next few years. So we gradually lose, at least for ozone, the ability to test the GCOS requirements. So I wondered how C3S, I'm very happy to see the in situ project as part of C3S, but I wonder how C3S is weighing on the insurance of these observations in the next few years.
If I can start answering, I think that this is a matter of discussion during several meetings within our contracts, but it was made clear, and I think also the other can contribute to the answer, that there's a huge interest by C3S in continuing this activity and to provide more data products. But the support, as far as I understand from your question, I hope I get the point, to support the long-term observations is not the role of C3S, but is instead the role of the European infrastructures, for example. I would say that a substantive part of the observation which are provided to C3S comes from networks which are satellite or part of ACTRIS, the European Infrastructure for Aerosol Clouds and Trace Gases, and so somehow they are supported. We also insisted a lot in trying to opening a discussion channel with through European Environment Agency, with the European Commission, to make clear that there is a need to support some strategic activities beyond the European infrastructures. But this is a bit beyond the role of C3S, which, however, has a huge interest, so can really endorse such kind of initiatives to ensure the long-term sustainability of the observations.
You also addressed it at me. So I would say that GCOS always has a interest in long-term observations and in the preservation of observing networks, and if you need help, you can always reach out to the GCOS Secretariat. I would note that the rolling review of requirements, there is a misconception that any single observing system needs to meet those requirements. That's not true for climate applications or any other application in the WMO rolling review of requirements, which is where the GCOS requirements come in. It's the totality of the observing system that must meet that requirement, and that is why, despite Copernicus nominally being a space program, it is essential that we do not take our eye out of the ball of in situ observations. In situ observations must be made, curated, and presented as part of a holistic climate service. They are an important component for reasons that, for example, Steve gave in his talk.
Yeah, thank you very much. In a sense, I would like to pick up from your very thought-provoking and engagement talk, Steve, because I saw a lot of nodding from Lothar, who was sitting on my side at your talk, and from what Peter is saying, the reanalysis has already been taken on board heavily in the IPCC. But what comes out of your talk is the fact that this is a snapshot in time, and for some ECVs, maybe reanalysis is good enough already. For some other, may become good in 10 years' time. So my question to all of you is, how should we set up a mechanism to systematically review that balance and update the recommendation, if you want, and what could be the role of GCUS or the IPCC or C3S in that process? Thank you.
Thank you, Carlo. Lothar?
Yeah, and I may start on this. I fully agree with Stephen that it's probably obvious to do the things more holistically. It's not a question on here, the satellite ECV product there, the reanalysis, because it's basically the same thing, the same physics, the same expertise that you need. It's maybe the difference is the direction. And so this combined approach is I think, the way to go, to combine the expertise. In the SAF network, we have a tradition with the NWP SAF that is exactly, let's say, at this borderline, and also working on the observation operators. And I think this is even more important also for maybe also for other SAFs to contribute with observation operators in order to compare the things and also to ingest the right information in the right way. The other aspect is our observations from satellite or in situ to validate the model. And here, of course, it's important to have the things in contrast to that, what I said before, separated. So to have not the satellite products maybe ingested with NWP information, to be completely independent on that. And that adds to the complexity, to what I mentioned in my talk. So there might be a good reason to have satellite products that are not using the best prior information from NWP to be independent in order to act as a let's say, a validation reference to whatever model observation is. But we need to be very clear what is the purpose, what is are the characteristics of our products related to the purpose that we intend.
Any reaction on the panel there, Fabio?
If I can, I want to add just one element that I tried to stress during my presentation, but don't be worried too much about, is uncertainty. You know? Because we have, I think, two ways to work more to ensure that the validation of reanalysis with in situ and satellite measurements are properly made, that this implies to quantify properly the representativeness of the gridded reanalysis data sets. And that's one step. The second step would be also to see some more, let me say, consolidated or closer to what we can define an uncertainty from the reanalysis. I know that it's a challenge, and I know people are working on that, but definitely these are two steps to ensure that we can define an ECV data products, which is still now a quite general, quite broad definition, but ECVs means to look at GCOS, and GCOS requires stability, resolution, spatial and temporal, and uncertainty.
Thank you. In the interest of time, I'm going to get another question. Alison?
Hi there, Alison, working in the reanalysis team at ECMWF. So thank you for a great set of talks. My question's really for Lothar. You mentioned the OSCE SAF dataset, which is fantastic, and I'm currently using that because we're going to be using that in ERA 6. But we have some issues with missing data in the 80s and 90s. I was wondering, in terms of an ECV and a consistent, complete climate data record, whose responsibility is it to gap fill those, or how will you do that? And especially, moving forward with other ECVs and even forward in time, if there are more missing data, how are we going to handle that to have a climate data record?
Yeah, great question. This is indeed important to have our, let's say, the data records also extended to the past, to arrive to longer time series. And basically, this is a great example of the network character of what we organize, because here, on providing the input data to the sea ice observation, particularly in the microwave, there's a great dependency and collaboration between the climate monitoring staff and the OC staff as a user. So within EUMETSAT, it's a shared responsibility that also includes, let's say, the competence and even data management in our headquarters in Darmstadt, the CM staff and the OC staff, and also are to exploit activities that are done outside EUMETSAT in other projects in order to have a better system in the future, in line of what I presented, a new version, extended temporal coverage.
Thank you very much. I think the debate has been really fascinating, and we can follow on in the coffee break. But I think now we need to close the session, and I ask a round of applause for this panel. Thank you very much.
All right, before we go to the coffee, we will also present some posters on the first floor there. So, and to be able to give all the people who will present these posters the opportunity to present what they have been doing, I would like to invite them to share a few words about their posters. So the first person is Françoise from CLS. Françoise.
Thank you. So the poster presents the sea level data set, which is an ECV of the ocean. So the sea level measurements are from altimetry satellites since 1993. And we provide this year a new reprocessing of the complete time series to the users by the end of the year. These reprocessings take into account new algorithms and methods that are provided in the poster. And the poster has a part also concerning the sea level indicator, which sea level rise, which is a good indicator of the climate. And it presents the acceleration of the sea level rise during the last 10 years. So I invite you to discuss about it in front of the posters. Thank you.
Thank you, Françoise. The second poster will be presented by Alena from OECD.
Thank you. I would like to present here our C3S soil moisture service. This service provides satellite surface soil moisture measurements based on large number of active and passive microwave sensors. It is based on CCI methodology, which is then adapted also for near real-time use. So every 10 days, we process the latest data. We have a global, daily, 10 daily, and monthly measurements that you can download from CDS. And at our poster, you can find more about this product. And you can also see there the newest validation results. Thank you.
Thank you, Alena. And I would like to ask Fabio to come back on the stage for his poster.
Okay, thanks. In the poster, you will find a second part of the story of the in situ datasets in C3S. In this case, most of them already published. It's related to climate data references. So The first part of this poster is related to the benefit of having climate data from a reference network, and you will see also some published application in peer-reviewed literature. And in the second part, instead, you may have a chance to have a look at the performance, or let's say at the features of the improved homogenized upper air data holdings we provided to C3S. So generally, I would say all of them are reference information for the study of climate and for the validation of other data sets.
Thank you, Fabio. Peter?
Thank you very much. So I carefully checked all the posters, and I'm delighted to announce that our poster is the only poster endorsed by Arnold Schwarzenegger. If you want to find out why, please come to our poster. And remember, Arnold is very upset because not only did his football team lose like the Belgians, but they lost to an own goal. So please don't upset Arnold, come to our poster.
Thank you, Peter. And Alina has a second poster. Oh, no, it's first Gerard, of course. Kenemai.
So in the in situ contracts, we like to think that we are providing some of the ground truthing of the wonderful C3S products. But are we doing enough? So I think what the wet conditions of the past months in Europe has shown us is that we might need to step up our efforts when it comes to sub-hourly or sub-daily precipitation. But the networks of the Met service are actually not sufficiently dense to provide that. So the poster gives a way forward, how we might be able to provide some of this ground truthing for C3S. And it gives you some of the places where this works and some of the places in Europe where it perhaps doesn't work. Thank you.
Thank you, Alina.
Hello again. I would also like to provide an overview of our land hydrology and cryosphere service of the C3S. In there, we provide ECV products over soil moisture, as was already presented, and then also lakes, glaciers, and ice sheets and ice shelves. We also work on improving these products continuously. So, for example, in the latest version, you can find new products for the ECV's ice velocity and lake water level. And at our poster, you can find more information about all the products that we provide. Thank you.
The next poster will be presented by Jan.
Thank you. Hello, I'm Jan Weite from Envio Environmental Earth Observation in Innsbruck, Austria. I'm here on behalf of the C3S Ice Sheets and Ice Shelf Service, which is currently still part of the combined land hydrology and cryosphere service. Our poster highlights the ECV products or quantities that are generated within our service. And these are derived by multiple satellite platforms. And these are really the only way to get consistent long-term continuous climate data records covering the vast ice sheets. So our service provides three types of products. So first one is ice velocity. This is provided as annual maps covering both the Greenland and Antarctic ice sheet also since last year. Then the next one is surface elevation change, provided as gridded monthly maps, 25 kilometer resolution, and derived from satellite altimetry. And then thirdly, gravimetric mass balance, which is provided as gridded maps of mass change, covering both Greenland and Antarctica. And yeah, so I think maybe I'm a little bit biased, but the rapidly changing ice sheets are perhaps one of the most iconic symptoms of climate change. And I think our products provide critical information to assess the current state and future state. Thank you.
Thank you. And it's Bart who will present the next one.
Yes, hello, good morning to everyone. So I'm not Michael Morros, that's my colleague who couldn't be here, unfortunately, but no problem. My name is Bart Ronde, also from Vito, and I'm happy to present you our poster about not less than 7 ECVs, or ECV products, which is we have the vegetation ECVs with LAI FAPAR land cover, an energy ECV surface albedo, and then 3 fire ECVs, the active fires, the burnt area, and fire radiative power. As usual, the different products are a bit in different stages of production. This summer we try to catch up with the vegetation products. And so the consortium is led by Vito, happily supported by Brockman, EOLab, the University of Alcalá, the Catholic University of Leuven, and IGEOS. I hope I don't forget anyone. So welcome at the poster.
Thank you, Bart. So enjoy your coffees, go and see the posters, and we're all back at 11:30.
Okay, if you would take your seats, please. Welcome to this session on reanalysis, which will last an hour. I'm Bill Bell. I'm in the climate reanalysis team based at ECMWF, happen to be based in Bonn. We've got 5 talks lined up for you, followed by a panel discussion. In those 5 talks, we have 2 that are really concerned with the status of our preparations for the next generation global reanalysis, ERA 6, and also the status of our regional reanalysis plans. But those 2 talks will be preceded by, firstly, a talk on the study that's ongoing at the minute, on the value that we extract from ERA 5, specifically the economic value. And then the second talk in the session, which will be given by Alison Cobb, is on how we gather and harvest user requirements in specifying what ERA 6 looks like. And then finally in this session, we've got a talk from Patricia de Ronne, looking forward to ERA 7 and some of the scientific developments that are underway to improve the coupling of the land and atmosphere. The first talk in the session is by Lef Mamet, who's the co-founder and director of Evenflow, based here in Brussels. And he has managed a study on looking at the economic benefit and wider benefits of ERA 5. So Lef, please take the stage.
Good morning, everyone. I hope you can hear me well with the system. Very good. So I'm Lefteris Mamais. I'm co-founder and director at Evenflow, and I'm very pleased and honored to present to you some of the key findings we have so far on the study we're conducting for ECMWF on the value generated by ERA 5. I should say here already that what you will hear, it's also to a very large extent the work of my colleague Catherine Mandler, who is the lead analyst, but couldn't be here, she's in the US. All right. So as with any investigation into the value that a certain data set or solution generates, the best way to confront stakeholders is to ask them a very simple question. What would you do if there was no ERA 5? And when we actually did ask this question during the many interviews we have done, what we found is that most of the stakeholders were falling into a sort of deafening silence. It was really intense. So now let's try to give voice to some of the insights we have collected and some of our own investigation and see where we got. So the objective that we had when we started studying the value generated by ERA 5 was to assess the benefits resulting from different types of uses. And the way to actually do so was to follow a combination of a bottom-up value chain approach, where we were actually adapting the methodology we had developed, co-developed actually with ERSC on the Sentinel Economic Benefit Study, and a top-down microeconomic investigation, which was helping us to validate our findings. This was applied across 10 cases, you will see more about that in a moment, in 9 sectors. And what's really important to highlight already here is that here we were really trying to look into cases that we can really establish the delta from ERA 5, not speculative sort of approaches. So for the implementation, we have conducted more than 75 interviews. I think it's 78 at the moment. We have conducted also, of course, extensive desk research, and all this has come together in a full comprehensive report, which is currently being finalized, and a visually attractive companion. You can see also on the bottom the different types of benefit. It's not only economic that we have been looking into. These are the 10 concrete use cases that we looked at. And the whole idea from the bottom-up part was that we were looking into those and extrapolating into a much larger set of, let's say, boundary conditions so that we could establish a bigger picture. Today, because of time constraints, I will only be focusing on 3 of those. So let's try to translate the delta that ERA5 generates. And let's start with offshore wind energy optimization. As many of you may well know, the REPowerEU initiative is actually asking for a rapid acceleration in the production of energy from renewables, and in particular, wind farms. But there's a high capital cost in developing these wind farms. And in that sense, increased certainty in the wind energy production potential is of the essence. This is exactly where ERA5 comes in. And the value chains we have been looking at involve service providers or representatives from academia who use ERA5 to provide to wind farm developers and machinery manufacturing, actually, analysis which help them identify the ideal locations for the wind farm and predict the wind energy production potential, but also inform things like the ideal spacing between turbines. And through the interviews we have conducted, but also through extensive analysis of the available bibliography, we have come to the conclusion that there is a 20% higher accuracy enabled by ERA5 on the basket of parameters that is relevant here to evaluate the performance of the wind farms. And this is then translated into reduction of the risk of excessive capital expenditure, cost save, and efficiency gains in this whole process. How much does this actually amount to? So the average reduction of risk, thanks to ERA5 in this particular case, accounts to 2 to 3% of financing costs. And here we're looking into savings to equity. In practice, this comes up to approximately 7,000 euro per megawatt. And what we did is that we did a very detailed analysis. So we took all the farms that have been commissioned from the moment ERA5 was released up to 2023, so 2018, 2023, in the North Sea, and then extrapolated over the whole of Europe to find an ERA5-enabled benefit of around 30 to 33 million per year. As I mentioned, it's not only economic benefits, it's also other dimensions. Here you see what is probably obvious, the regulatory. So it does help to achieve the goals under REPowerEU. And here is a quote, which is a standard quote. I see some of you are also from that sector, so you will probably relate to that, from a wind farm engineer, of how essential ERA5 is in this process. Looking now at a completely different facet of how the value manifests itself, we want to dive into how we can exploit scientific findings, which are informed by ERA5, in policy recommendations, but also in raising public awareness. And here the challenge is that there is intrinsic complexity in the climate system, you know it better than I do, which basically tends to create a situation where most average people cannot really understand what this means for them. And on top of that, they actually tend to downplay or completely disregard it, as we can also see from the recent results of the European elections. So at the end of the day, this directly impacts our ability or inability to draft policy in an effective manner and to actually act meaningfully on an individual basis or as a society as a whole. And where does ERA5 come in here? ERA5 is the key dataset, or in many cases, a backup verification dataset for climate systems modeling, depending, of course, on the aims of the research. And in that capacity exactly, it's where ERA5 informs by providing most accurate and detailed inputs to CMIP. CMIP itself is an essential part of things like the IPCC assessments. It's about half of the content, actually, it's informed by CMIP. And that in itself provides a very important foundation for policy formulation. At the same time, and I believe you heard about that very well this morning, ERA5 informs some of the essential climate variables, which are used in this type of IPCC assessments. They are also used to communicate things around the environment in an easily understandable way in things like the European and the WMO state of play for the climate. All of that, it's actually setting the foundation for public discourse, so for the dialogue on these subjects. Here, what we did to actually pinpoint what is the value of ERA5 is use a value of information approach This was making use of page 09. This is quite technical from an economic perspective, but probabilistic integrated assessment model. You see here some of the references. And this actually looks into the impacts of climate change and the costs of abatement and adaptation to climate change. So when we annualize and apply this to this particular time frame that we're interested in, using also input from Systems Change Lab, and when we then try to find the share of ERA5, taking into account the input from our stakeholders that we interviewed, and also technical articles, we come to a very conservative rate of 5 to 10% for ERA5, which then means that the scientific output informed by ERA5, which then feeds into policy formulation on one hand, and into public awareness via media, amounts to around 90 to 180 million annually in the first case, and 70 to 140 in the second. At the same time, and this should come as an obvious reflection, this represents a major contribution on science itself. Many cutting-edge science publications and also the citations that they have, these are good proxies. And likewise, many of you might have witnessed the fact that references to ERA5 in the media have skyrocketed in recent years. So all this gives you just a taste of how ERA5 generates value and how we have been analyzing it. There is much more, and this much more you can actually one day see through the final report that we are preparing, and likewise through the attractive e-report. And also, since this is kind of part of the scope of this session as well, we have collected input from practitioners on limitations, but also on future expectations vis-a-vis ERA6. And with that, I would like to thank you for your attention. I would like to acknowledge the support and guidance we have received from many of you and many ECMWF colleagues, and of course, our collaborators in the project, Min Paris and Murmuration. Thank you very much.
Thank you very much, Lev. Thank you very much for a super clear presentation and a really quick presentation. If you just hang on a moment, because I think we've got time. If anyone's got a burning question, there'll be another opportunity to ask Lev at the panel discussion. But if you've got a question now, we can take a quick one. Yep, there's one at the back there.
Thank you for the presentation. It was really interesting. You just said that you're focusing on a few of the different cases you looked into. I was wondering if you could say a few words about, not the findings of all of them, but if this was consistent across all of the different cases you looked into.
Sure. So we have been looking into different sectors. You saw a slide about that. The important thing here is that you cannot use one approach for all the different sectors that are analyzed. So for instance, we have been looking into ML and AI, where ERA5 is used to train different data sets by different companies, actually some very big players, which generates a completely different type of value, which you then can monetize in very different ways than the ones you saw here. We saw also things like tourism and cultural heritage in Malta, which was a very interesting case. Water management, agriculture, I mean, I could be talking on and on. And again, all of the cases we looked at in these particular sectors were cases where we could really pinpoint the delta from ERA5. This is important because otherwise one has the risk that they're starting to talk about something that is not really there.
Thank you very much. Leaf, that's, oh, sorry, one quick more question. Yeah, on you go, Dick. You need a mic.
Just to clarify, can you tell me exactly what you mean by delta? Is it delta against an alternative reanalysis or delta against no reanalysis at all?
It's actually both, depending on the case. So in certain cases where you have no counterfactual at all, you need to really pinpoint, for instance, which particular parameter that ERA5 provides is the one that helps create some increase in performance, in efficiency, and so on. So we have seen, for instance, for nighttime parameters, or we have seen for temperature. So in other cases, we are looking at exact counterfactual versus MERA2, for instance. So it really depends on the case.
That's great, Lev. Thank you very much. It's really a powerful analysis as we look for justification and motivation for continuation of the programme. Okay, our next talk was due to be given by Delphine Daring, who's ECMWF. She's been looking at harvesting user requirements and defining next generation reanalysis. She came down with COVID, tested positive yesterday. We hope she gets well soon. But Alison Cobb has stood in at the last minute and agreed to give a summary of Delphine's talk. So I'll invite Alison to the stage. Yes, you. No, it's you then, Hans. Yeah. It's Hans. Okay, sorry. It's Hans next. Hans is the leader of the ECMWF Climate Reanalysis team, and his talk is going to be about how we have planned ERA 6 and the production schedule.
Well, thank you very much. So apparently the order of the talks was changed at the last minute, but that's okay. I will talk about where we are with ERA 6. So my name is Hans Hersbach. I'm in charge of the ECMWF Climate Reanalysis team. I would particularly like to mention two new people that have recently joined our team, which are Alison Cobb, who will give a presentation soon. She is working on diagnostic, but also interacting with user questions, because we have a lot of users. They ask a lot of things. We learn a lot from them. And Mikko Kaandorp, who is working on data simulation methodology, and at the moment particularly on the ensemble data simulation that provides the uncertainty estimate, will provide the uncertainty estimate for ERA 6. Okay, so ERA 5, that's where we start from, hourly resolution from 1940 until 5 days ago. And it was really built on the shoulder of other ECMWF reanalysis. So you can see that at this plot, which will be a figure in yet another ERA 5 paper, which was actually accepted for publication last Friday evening. And higher is better. So you see that each reanalysis is building on the shoulder of the others. You get better and better. Not only that, ERA 5 is the reanalysis that covers them all over all periods and even longer. And then, of course, each reanalysis itself was based on the state-of-the-art NWP at the time at ECMWF, which is the result and stands on the shoulders of literally thousands of researchers that have worked at ECMWF over the past 50 years. Okay, so we have a lot of users, 160,000. So those are not just people that are not people that are reading the news or the people on the street. It's really people that have been downloading and working with reanalysis. To get an idea, what does that mean, 160,000? So you have to connect to an all-day situation. So look outside, maybe football, European football. So we have the mid of July, we have the final, and suppose that your favorite country is playing, together, of course, with the Netherlands in the final. And suppose that the audience will be filled with only with ERA 5 users, and they're doing this, and they zoom in the TV, and you see these people, the ERA 5 doing the ERA 5 wave, and there's massive amounts of people. Well, you would need 2 stadiums to fill all of all the ERA 5 users, and not even that would be enough. You would still need the overflow with the big screens, people working on the big screens because they didn't get a ticket. So that's what 160,000 people means. So it's a lot of people. Okay. So of course, ERA 5 is used a lot. So also by C3S, we was discussed yesterday, a very nice session. So we look at the news that typically says source C3S ERA 5. So ERA 5 is used for a lot of the data that we use ourselves. We use is based on ERA 5. That's for climate monitoring, but ERA 5 is also used for a lot of applications where actually the actual weather of that particular case is important, not just the climate variability, but actually the real synoptic situation. So that ERA 5 also provides, and also extreme cases. And then, of course, we have now that the last few years, ERA 5 has become the leading training data set for data-driven weather forecasting, which really is a revolution in how we maybe will do numerical weather forecasting in the future, and much more. Okay, so that's ERA 5. Let's go to ERA 6 now. So ERA 6 will benefit from an additional 8 years of R&D at ECMWF, and also we make use of improved compute power. That means that we can go to 40 kilometers. So ERA 5 was 31 and the waves were 40, so there will also be 14 kilometers now, which will give a better estimate of extreme weather. So the uncertainty estimate will be at 28 kilometers. It's also more than double what we had in ERA 5. Well, science. So one of the big things is that we will have a one-way coupling with the ocean. So we don't do the data simulation of all the ocean observations. We don't do that in ERA 6. But we will harvest that, and that is a reanalysis called ORA-S6 is being produced as we speak, and we feed that into the ERA 6 reanalysis. We have more improved reanalysis, such as realism like introduction of an urban tile. We have better ways of treating systematic model errors, which we can improve the fidelity of climate trends, especially in areas where we have less direct observations, like in the stratosphere. And we also resolve a number of ERA 5 known issues that are all listed on our web pages, like, for instance, the inconsistencies we had in snow cover. That will be much better in ERA 6. Okay, we ingest the best observations, because without observations, there's no reanalysis. You need the observations. So that's a really important point as well. So that involves satellite reprocessing, but also data rescue. We do that together with our C3S contractors, which are all here. And one nice example of data that we'll use in ERA 6 are these surface observations over Greenland, where we didn't have, I think, hardly any of those observations. And those are direct observations. You have satellite observations, but also where you have the direct observations, it's really important, especially in this area where climate change has been ongoing so rapidly. Okay, then finally, products which are based on user requirements. We will have hourly, but we have more parameters like clear air turbulence, which has recently been in the news with several aircrafts being in trouble because of the turbulence. Will it get better? Will it be worse? Was it better in the past and worse now? So this is something with reanalysis. You can do a trend study. We will height levels, which is easier for non-technical users to use. And we will also have daily pre-calculated statistics rather than only monthly. Okay, so that's what we will do. So how will ERA 6 look like? So some preliminary results. So first of all, the resolution. We go from 31 kilometers to 14 kilometers. So if you do a map of the orography, you really see that you get much more details over the Alps. But then resolution, maybe that's just a map, but maybe, reanalysis, these models, they're all smoothed and so on. So maybe it looks nice, but in reality, it's still very smooth. So one way to study that is to look at energy spectra. And that's what we've done. So when you look at energy spectra, you see total wave number and the energy. You see ERA 5 at some point it's getting less, you have less energy in the small scales, that means it gets smooth. And with ERA 6, you go much further. You see there's a TCO 609, TCO 709, it was 80 kilometers and 40 kilometers. There were two options we were testing. At the end of the day, we decided to go for 14. And we get a giant step, and the 14 just gives this little extra step to make it a much better product. Okay, so that's a small scale variability, but then you can say, wow, noise is also small scale variability, as that doesn't prove anything yet. So let's look at some real cases. So one good case is like tropical cyclones. So that we have here. So you see that the TCO 709 will be the ERA 5 grid. Resolution has the best winds, and also when you look at the relationship between the maximum wind speed and minimum pressure, and the black line is IB-Trex. Those are observational bogus data. You see that the curve will go from ERA 5 to ERA 6 is much closer to IB-Trex, and it also goes further into the extremes. So yes, the small scale variability, high resolution, it gives us more extreme and better representations of these extreme cases. Then, well, this is a very technical thing, but when you combine observations with models, you want that every time when you correct the model, that the observation you do a little bit, correction. You don't want that you systematically, you're always correcting in one different way. And when you do that, you can run into trouble. And so we always want to see that these systematic increments, that they get smaller and smaller. This is a very complicated plot where you look at the power statistics for one satellite, which is sensitive for temperature in the vertical. But basically, the message is when you're closer to the zero line, you're doing better. Your systematic increments are smaller. You clearly see that for ERA 6, the systematic increments will be much smaller. So again, also the better way we treat model error, systematic model error, that will be improved. I talked about the ocean, the Aura S6, that does all the ocean, but it doesn't do the big lakes like the Great Lakes, so we have to provide some additional information for that. So we're looking at that as well in detail. So because for ERA 5 over the Great Lakes, in a period between 2007 and 2014, we didn't really do a good job. And we had this inside joke saying that ERA 5 inferior over Lake Superior. So we want to do better here now. So we looked at a number of data sets that are available, ECV data sets. And we found that for SST, the Ostia reprocessed data is the best one, and the OCSAF reprocessed data set is the best one to use for sea ice. So that we will use in ERA 6. And finally, there is the ocean. So it's all hourly again, so we get the SST, the sea ice, but these are ocean currents. We didn't have that in ERA 5. So you see they evolve hourly, you see how the eddies move, but you also see how the weather, the weather on shorter timescales is affecting these ocean currents. And these ocean currents, the whole ERA, this is actually, although we get the data simulations done in Aura 6, where you get all the ocean observations in, but then in the data simulation system of ERA 6, there's always observations, there's also always a little bit of a model part, and that model part we couple also with the ocean. And there, we will make these ocean currents, they will be consistent with the whole atmospheric boundary layer. So the atmosphere really knows consistently about these currents. And for ocean waves, you have wave refraction, like swell. They can travel thousands of miles where you have big currents over the tropics. They will deflect, and when they arrive at Portugal, they can be a completely different location. So again, ERA 6 with the ocean currents will improve that. I'm probably over my time. 1 minute. Okay, I have only one more slide. So this is just a bit of a showcase what we think ERA 6 will look like. My final slide. So ERA 5, hourly snapshots, over 84 years, very popular. But we go to ERA 6 now. We are finalizing the scientific configuration as we speak, and we are performing extensive in-house evaluations. Then, in addition to that, we have made an ERA 6 prototype dataset available to a selection of reanalysis expert users, because at the end of the day, they are our users. They know what is important for them, and we asked for their feedback. Production, when we start the production of ERA 6, we're working towards to start early 2025, and we will do the most recent decades first. Then at about towards the end of mid-2026, end of 2026, that will be finished. We will make that data available. In the meantime, we're already starting to work with production of earlier decades, and we will then adding further decades in stages until by the end of Copernicus 2, we should have data from 1950 available to users. With an ERA 6T, 5 days behind real time included as well. And our final message is that the future operational Earth system reanalysis continues to be aligned with the NWP at ECMWF, and it's really, a lot of synergies is being done there. And part of the work that is done there is based on external funding like the ESA CERA and ERACLIM2 and the European Union CONFESS and CERES projects that Patricia will talk about later. Well, thank you so very much. Yeah, I talk too much. Yeah. Okay.
Thanks, Hans. Yeah, we'll move on, and hopefully we can pick up questions at the panel discussion. So Alison needs no introduction because I gave it 10 minutes ago. But she has recently joined the reanalysis team in the last few months, actually, and she's picking up some model aspects and user requirement and user support aspects. So Alison, carry on.
Great, so good morning everybody. I'm going to be talking about taking on board user requirements. So a nice follow-on from Hans's talk from ERA 5 to ERA 6. So as we know, C3S is user-driven, so we need to collect user requirements. Sorry, I'm not sure what's going on with the slides. Half of them are missing. Oh, there we go, that'll do. So this flowchart shows how we collect those requirements. You can see on the top left, we've got 5 channels for gathering such requirements. These include feedback by user support channels, focus groups, workshops, training, and the Copernicus User Forum. And we have 4 focuses for these requirements. They include datasets, sectoral and user-specific, tools, and service development. So once we've collected those user requirements, we have them in a requirements database. And with that, we manage it and analyze those requirements, producing reports and documentation, and then finally implementing them, so within the service and informing future evolution. So one key part of gathering requirements is having workshops. And last October, we had a very successful online workshop entitled ERA 6 User Needs. As we know, with people represented here, reanalysis users are very diverse. And we had 24 external participants, including key users and stakeholders spanning many different research areas, including climate attribution, ocean modeling, IPCC assessment, weather forecasts, and machine learning. We had representation from a number of different sectors, including agriculture, food security, renewable energy, and health. We had representatives from broader climate services for adaptation, the European Commission, as well as ECMWF experts. Within that workshop, we had 4 different breakout groups, the first being data quality and robustness. And the objective here was to discuss potential new versions of ERA 6, post-processing needs, and quality assurance requirements. Another group was the technical aspect, so discussing the challenges with moving from ERA 5 to ERA 6. We had application, so enhancing the applicability and user uptake of ERA 6, and the objective here was to share experience on the use of ERA-derived products and requirements to enhance ERA 6 applicability and user uptake. And finally, R&D and long-term needs. So this is setting the path to ERA 7 and beyond. The objective is to discuss research and development investments to develop future reanalysis. So knowing that not everything can be done in the next step for ERA 6, but taking on board those requirements, looking to the longer-term future. And so finally, here are the key messages. The top priority for ERA 6 is higher spatial resolution. And as we can see from Hans's presentation, that we're already doing that, going to 14 kilometers, and enhancing accessibility and usability. So ERA 6 already provides several improvements, including all of those technical improvements that have been done by R&D over the past 8 years. We need tailored post-processing tools to support users in transitioning to ERA 6. And this includes facilitating performance diagnostics and quality evaluation, support for visualization, and quantification of biases. So those are key messages that came back from this user feedback. Many requests regarding applications are already covered by C3S services and products portfolio. So C3S is ahead of the game, but needs to further enhance its outreach activities to ensure relevant users are always aware of what's available. And finally, full representation of the Earth system with full ocean coupling to represent feedback processes is a long-term requirement towards enhanced reanalysis quality and to reinforce the vision behind ERA 6 and ERA 7. That's it, thank you.
Thanks very much, Alison. I think in the interest of time, we'll move on. We'll come back to the panel discussion for questions to Alison. So the next talk is by Andras Horanje, who is a former member of the reanalysis team based at ECMWF. He's recently moved to climate projections and predictions, and he's also the technical officer for the regional reanalysis contract. So, on you go, Andras.
Okay, thank you, Bill. Good afternoon. It is my pleasure to welcome you to this presentation on regional reanalysis. I am happy that I can give you this talk on behalf of my co-authors, because I understand that ERA 5 and then 6 gets all the spotlight, all the attention, but I think the regional reanalysis, and I try to demonstrate for you today, is also important for us. Carlo mentioned in his opening talk, and I try to give you some evidence that this is the case. Yes, for my co-authors, I have people from ECMWF, from the reanalysis team, Cornell, who is coordinating the work together with our contractors for the European regional reanalysis, Hans, of course, who is the main person in reanalysis for us, and Matt Chantry, who is liaising us with the machine learning community. And I would like to mention our contractors who are leading the European, the Arctic, and the Arctic regional reanalysis, Samuel Szymanka and Harald Schieberg. And in this plot, I just give you a flavor, and I will give you a bit more what improvements regional reanalysis can give with respect to the global reanalysis. First of all, okay, a large part of this slide covers ERA 5. I don't want to dwell on ERA 5. You know everything about it. But this gives you an idea about the zoo of reanalysis data, what we provide through our C3S climate data store. And of course, the regional reanalysis is not independent of the global reanalysis because it is embedded to ERA 5. The lateral boundary conditions are taken from ERA 5. And the regional reanalysis applications try to add more value through various ingredients. And in blue, you can see the list that they try to describe better the surface characteristics. Most importantly, they have local observations which are not included in the global reanalysis ERA 5. And they have a model which is a high resolution model, and they have expertise, and they are tuning the model to the region of interest where they are running the regional reanalysis. So we have two kinds of regional reanalysis for C3S. The one in the left is for the European regional reanalysis. We shortly call it SERA. And this is for Europe, as the name suggests. I just give you what kind of data we have. Maybe I just emphasize that it includes an ensemble of data simulation. So it has an ensemble to provide uncertainty estimate for the data. The other one is the Arctic regional reanalysis, which is covering the Arctic region at the moment for the European part of the Arctic, and in the future about a pan-Arctic domain. I will dwell a bit on this a bit later. In this table, sorry, the table doesn't look perfect, but I think the main message you can see. And these are some details what this regional reanalysis bring to us. For the European one, you see the resolution, ERA 531, and the European one is going to 5.5 kilometers for a region over Europe. It covers the area from 1984, and hope we lost something, but only ERA 5 lost, so that's not a big loss at the moment. And we are expecting to have some timely updates in the coming, in Q1 2025. And I spoke about the EDA, and we have a land component called SERA land. And the main plan is, for the future, is to go backward, so to go back to extend the data set, to back-extend the data set till 1961. The other regional reanalysis is CARA, Copernicus Arctic Regional Reanalysis. We call it CARA, or CARA 1 and CARA 2. It's available from 1990 for the European part of the Arctic at the moment. It has a timely update procedure, which means that in 2-3 months, we provide a new 1 month of data set to update, to extend the data set with near real-time data, and it has a very high resolution of 2.5 kilometers. And I will demonstrate a bit later what does it mean. But before that, it's just to mention that we are working, or our contractors are working in CARA 2, which is the Pan-Arctic version of, I am afraid I cannot go back, no, I can, which is a Pan-Arctic version of the Arctic region reanalysis, which will cover a much larger domain, shown in blue, and a full Pan-Arctic coverage. Okay, so that will contain again 2.5 kilometer resolution. The drawback or the disadvantage of CARA with respect to CERA and ERA5 that you don't have an ensemble of data simulation. So the uncertainty estimate is done in a different way, but there will be some advanced method for CARA 2. And if you want to get more details, we have here Harald on behalf of CARA and Semyon on behalf of CERA. So they have poster. Harald has 2 posters, so feel free to visit them upstairs in the posters. And there are some references. I hope you will see better in the PDF after the workshop what you can see. So this is just really one slide to show what you can expect from regional reanalysis with respect to global one. On the left, you see a comparison of ERA5 and CARA about precipitation. So you can see that in CARA, in the middle image, you can see much more details. And in the difference, you can see that the precipitation is more extended into the Greenland continent in ERA5 with respect to CARA, and the peak is smaller in ERA5, and it's nearer to the reality for CARA. The other peak, it is my personal favorite, you might disagree, but this is a plot of horizontal and vertical speed for the Arctic region over the Greenland area. In the colors, you can see red and blue the vertical speed, updrafts and downdrafts, and you can see a lot of details over south of Greenland. And I think the nice thing, what I really like, this updraft jet on south of Greenland. So this is so much tiny detail what you will, I should say, never see in global reanalysis, but I'm scared to say it in front of Hans. So I think it's quite astonishing, and it demonstrates quite well that what kind of details you can get. And I learned in the last few years that a talk cannot be complete and good enough if I don't speak about machine learning. So my 2 last slides will include some information on machine learning. Yesterday you heard a bit from Athena, and she has a poster on this Code for Earth. It's a short challenge of 3 months where we invite some challengers to create some application for us. So the question was if machine learning can provide some supplementary information on top of the data what I have just described. And the idea was really to use ERA5 data and CERA, so the European Regional Reanalysis data set, for training a machine learning algorithm to provide regional reanalysis for Europe, of course, for a period which is outside the training period. So the results, in brief, that of course is compared to CERA. So there's a training for a given period, but we have CERA data outside this period, so the machine learning data is compared to the CERA data set outside that training period, and the results were comparable in some way, but of course there were some limitations that only 2-meter temperature and a smaller subdomain was used. But you could see, and I will show you in the next slide, some of the orographic features and coastlines were represented. This is just a snapshot to show you the same thing for European reanalysis in the traditional or conventional method, and with machine learning, you can see this is a domain over Spain and the neighboring some of the islands. You can see the Pyrenees is seen pretty well. You see the lengthy mask, the differences over continent and sea. So it gives a good idea that machine learning can provide some information, and that's why our next plan is, I told you, CARA and CERA provides data in 2-3 months delay. This is a bit too much. So we want to explore the possibility to use machine learning algorithms to provide data in a much smaller latency in terms of few days, 5 days, like for ERA5. Maybe not for every variable, but we are exploring this, and we will launch an ITT very soon to to find some people who can do with us and provide this kind of service. So Bill is anxious now, or I'm patient, so I stop now. Thank you.
Thanks very much, Andras. I'm sure we'll come back to the machine learning aspects in a panel discussion. But in the interest of time, we should move on to the final talk in this session, which is by Patricia Derone, who leads the coupled data assimilation group at ECMWF, and she's going to be talking about plans for developments on coupled DA for ERA 7.
Yeah, thank you, Bill. So I'm trying to switch. Sorry. So I don't know, it doesn't work to switch to the next presentation. Okay, thank you very much. So I'm going to talk about the CERES project. It's a Horizon Europe project which started in January last year for 4 years. We are 12 partners in this project. You see the logos at the bottom. And CERES stands for the Copernicus Climate Change Service evolution. So it's all about the evolution of the C3S tools. So the aim of the CERES project is to support the long-term evolution of the C3S tools for regional and global RNAs, as well as for the multi-system seasonal prediction, towards an Earth system approach, and with a focus on land-atmosphere coupling. So on the right, you see a schematic representation. You've seen it in Steve's presentation this morning of what is an Earth system approach. It means that we use a coupled model where we account for land, atmosphere, ocean, sea ice, wave. But we use a different data assimilation system to ingest observations in each of these components. We have a different data assimilation system which is adapted to the time scales and the processes that we have in each component. And what we do in CERES is to develop coupling between land and atmosphere, coupling in the sense of data assimilation, where we want to enhance the consistency between the land and atmosphere data assimilation system, with a key role of interface observation in this process. So land-atmosphere coupling, Hans mentioned ocean-atmosphere coupling. We've done great developments related to ocean-atmosphere coupled data assimilation supported by previous European projects, but very little effort was dedicated so far on land-atmosphere coupled data assimilation to do a better usage of observations and to improve the consistency. However, we know that the near-surface conditions over land are of critical interest for the users. You've seen this map, for example, for surface air temperature anomaly for May. It was in Hans' presentation, and you've seen similar maps yesterday as well. So it's a flagship product of the C3S service. This output temperature from ERA 5, for example, is extremely important for the users. It's used it is here from the climate bulletin, but it's also used for the European state of the climate or the global climate highlights. But there is an increasing interest also for other land surface related variables like air humidity, soil moisture, which is shown on the right, which is also part of the climate bulletin. So the quality with land atmosphere coupling, we are aiming at improving the quality of these surface and near surface products, and also improving the consistency of these C3S surface products and ECVs over land surfaces. So what are we doing in practice in CERES? We are developing land and coupled land atmosphere data assimilation. Coupled modeling and coupled assimilation is not the same thing. We want to find the optimal degrees of coupling which is required to have an optimal system in terms of representation of land surface and near surface atmospheric conditions. So it's illustrated on the right here. I will not go into the detail because it's very methodological, but it is an important part of the SORI's activities. We are exploring and developing machine learning-based observation operators to improve the exploitation of satellite observations over land surfaces. We are taking into account multi-decadal representation of evolving vegetation and lakes. So for this, we are building up on the CONFESS project, which finished earlier this year, but extending back in time, back to 1925, the representation of time-varying vegetation. And we are also developing the capability to use this time-varying vegetation and lakes for reanalysis purpose. A key aspect of the project, of the SORI's project, is to prepare the next phase of Copernicus. So we want to have a very high readiness level. Whatever we do, it needs to be ready to be used for reanalysis and seasonal prediction systems in the next phase of Copernicus. So we develop prototype, we deliver prototype of seamless reanalysis, global and regional reanalysis, and multi-system seasonal prediction. So high readiness level is extremely important. And finally, we are developing novel diagnostic tools to assess the physical consistency of Earth system reanalysis and Earth system prediction. You will see a demonstration this afternoon about the Sunset tool, which is being developed in SORI's to assess the seasonal prediction systems and their consistency. So exploitation of satellite observations. Currently, in the reanalysis systems, whether they are regional, global reanalysis from Europe or other continents, we completely underexploit the satellite observations over land surfaces. Both observations useful for the lowest level of the atmosphere, but also we don't use enough the observations that we have from many satellites to constrain land surface. So developing machine learning observation operators to better exploit the satellite observations means that we want to enhance the exploitation of past and current satellite observations over land in coupled Earth system reanalysis systems. So you see some examples of ERS or SMOS satellites. These are just some examples. There are many more that we don't currently fully exploit to constrain the system. And also to prepare for the future missions. For example, EPSSG and CIMER, which is one of the Copernicus mission. CIMER, which is extremely relevant for coupled data assimilation because it's low-frequency passive microwave, which is sensitive to the lowest level of the atmosphere and to the land surface and sea ice as well, and ocean surfaces. So time-varying vegetation that I mentioned before, we use constant maps for vegetation. I know it's not good, and we are all aware of this. So it's a key aspect of SORI's as well, in continuity with the CONFESS project, to represent these variations of the land surface, land cover, and also LAI in our reanalysis systems. Again, global and regional reanalysis. You see at the bottom right, it's a bit hidden, but you see the global area of different land cover types, even for the last few decades. There is a very strong evolution of this. So we need to take this into account to improve our reanalysis products from the next phase of Copernicus. And finally, time-varying lake cover. This is something new. It was not addressed yet in the CONFESS project. So we need to take into account the variations of water bodies over land surfaces to have an accurate representation of surface temperature locally in these areas, but also with downstream application related to the hydrological cycle. This time-varying lake cover is extremely important for future generations of reanalysis. So you see an example of the Toshka lakes in Egypt. It's a good example of varying lake cover. These lakes appeared in the late 90s. It is there in the south of Egypt. The scale here is about a few tens of kilometers. They appeared unexpected. It was unexpected in the late 90s after some floods, and they progressively, consistently disappeared until 2019 after a flood event in Ethiopia. These lakes reappeared again unexpectedly. So this is something that we want to represent in our next reanalysis systems. So finally, final slide, to summarize CERI's project in a nutshell, it's all about consistent Earth System C3S products. So improving the quality and consistency of the C3S tools, directly addressing the user needs for improved and more consistent C3S Earth System reanalysis and seasonal prediction products over land surfaces. And there is a website that I invite you to visit to have more information. Thank you.
Thanks, Patricia, for keeping to time. If you just hang on there, if we ask the organisers to start assembling the chairs for the panel discussion, we have a quick opportunity for a question to Patricia, specifically on the CERI's project, if anyone has a question. I don't see any hands. Okay, so if the 5 speakers would just move to the stage. The format here is we're running slightly late, but if you'll just be patient with us, we hope that you'll stick around for 15 minutes while we put some questions to the panelists. Lunch break's quite long, so hopefully that's not too painful.
To hear you.
So the format is we would like to first of all invite questions from the audience to the panelists. And just to seed some thoughts, I've captured a question, top-level question, here in this slide. So in defining the requirements for and characteristics of the next generation of reanalysis, what's gone well and what could we do better? So that's just to get you thinking. So it's open to you. Yeah, there's a question at the back. Is that Anka?
Yes, thank you. Can you hear me?
Yeah.
It's not related to that angle, but it's still about the uses of ERA 5. We have been encouraging people to use ERA 5 as an alternative to other products and reanalysis to initialize their predictions. And for long-range predictions, you probably all know that a heavy, large, expensive reforecast set needs to be built. The requirement in this field is not for accuracy as much as for consistency, and certainly not for accuracy in terms of spatial resolution. What provisions are we going to make for these people who've already invested in running these reforecast sets using ERA 5 and want to use the real-time component for as long as possible so they don't have to repeat the exercise? Have we looked into this? If not, I think we should make a plan for either evaluating the differences between ERA 5 and the upcoming ERA 6 from this perspective of consistency, or if not, to see what we can put in place to allow people to continue to get the real-time output from ERA 5 for as long as they need to.
Maybe you could just explain what you mean by this consistency issue in using reanalyses.
People initialize predictions at dates in the past using some globally complete fields. They use reanalysis typically, and we did persuade them that ERA 5 has it's a good candidate to use because the purpose of this reforecast set is to understand model biases. So model biases, if they're dependent on initial conditions, need to be consistent between the reforecast period where you can define them and quantify them and the real-time forecast where you want to apply the corrections that you define from that case. If you are going to use for the real-time forecast something that's completely different, what you know about model biases when initialized with ERA 5 is completely irrelevant. So you need to find another way.
So your question's about how we address the specific requirements related to consistency for these applications?
Yes, we have 2 contractors for C3S for seasonal who use ERA 5 because it has this near real-time component, who are going to be asking this question as soon as we pull the plug on ERA 5.
Thanks, Anka. That sounds like one for Hans and maybe Andras.
Hello. Can you hear me? Okay. So you were also asking basically for how long we will have ERA 5T still available. Is that something that implies that?
I can't hear you.
Sorry?
I couldn't hear you.
I can't hear you now.
She doesn't.
Sorry?
She doesn't hear you. If I can translate, I think Anke's asking about how we've addressed the requirements for consistency throughout the period of the reanalysis to support.
No. So we need the consistency. Effectively, what's valuable here is the near real-time component of ERA 5, and people have investing in using the historical bit and want to be able to use the near real-time component for the lifetime of the forecast systems.
Yeah.
What are we going to do when ERA 6 comes up?
Exactly.
Do they need to rerun the whole thing with ERA 6? Who's going to pay for that? Or do we continue to do the real-time component for as long as we have the same computers or whatever?
So this question we get quite a lot actually, about people being worried about we have this system with ERA 5 and they invested in that. And so at some point we have, of course, ERA 6, things are getting better, but at some point the ERA 5 will always be there, you know, what has been produced, but the ERA 5T at some point will stop. And then you can't just start using ERA 6T with already a trained ERA 5 because there's an imbalance there. So that's so we haven't really made a firm decision on that yet, how long we will maintain ERA 5T. But of course, we have to very clearly communicate well in advance what our plans are. And at the moment, we haven't done that yet. And of course, we're not going to just stop at just bang. We need to have a consistently long period of ERA 6 and ERA 6T already available, such that a number of users have already been able to migrate to the newer and better system. So that's my answer.
Anke's given the thumbs up symbol there, so I think she's happy with that. We've got a question from Jean Noel at the front here.
Thank you. I think it's a question for you, Lefteris. So you started with if ERA 5 did not exist, what would happen? And you mentioned a deafening silence, if I remember. During your conversations, did you also ask the question, what if you had to pay for ERA 5? Because, of course, we hope that the budget will always be big enough to be the best, to provide a good service, and to be free. But beyond 2027, it's probably okay. But we know that there are, the Green Deal, the climate agenda, let's say, is also in competition with other things in Europe. So I think it's an important message to convey to the Commission that it has to remain free, otherwise they may go to Japan. So I don't know if you had this conversation with the stakeholders you interviewed. Thank you.
Thanks. So yes and no. I mean, we did try to confront stakeholders with the question of willingness to pay, because it's a standard process in this type of analysis. In most cases, as it happens actually elsewhere as well, there is a positive response, but there's no ability to actually say how much would I be able to pay, precisely because they don't have any real anchor of how much they benefit from it. So the primary focus of the investigation was on the benefit side, not on the potential cost side. Having said that, there were interesting cases where someone was confronted with the notion of, if I were to reproduce the same level of quality in my information, what would I need to do and how much would that cost? This actually came through in the cases of ML or AI solutions for disaster management, for instance. And there, some of the companies that we interviewed, they didn't divulge the cost, but they had assessed the cost that it would take them actually for 2 years running their own systems and models to get to a similar level of information as ERA 5 provides for free. So even that, I mean, one can then start extrapolating how many engineers you would have to actually be running these things, how much investment in infrastructure that you would have an equivalent output, and so forth. So this is something we have been looking at in the study. Thanks, Leif.
Thanks, Jean-Noel. Peter has a question.
So thank you very much. Very interesting talks. And I'm glad to see more on adding value integrated products from the reanalyses, but both the ERA 6 and the regional reanalyses, for novice users, they're going to be drowning in data. And I wondered what thought had been given to aggregate products. So someone might want the global mean. Coming back to Steve English's talk, if we want ECV, CDRs of global means of things, where are we producing these global means or these national means or these regional means, these products that might not scare the bejesus out of novice users and might see greater uptake of reanalysis data rather than just plonking daily, monthly, hourly data at ridiculous resolution and saying, good luck, folks. I mean, if we're going to be a climate service for everyone, where is the thought to design and output of aggregate products that actually might massively increase user uptake?
Thanks, Peter. So the thought given to aggregation of fields, that's probably Andras, Hans, Alison. Andras had his hand up first.
Yeah, sorry, it's not more, it's just an information what you might not be aware that we are developing the Copernicus Interactive Climate Atlas, which is able to provide information on reanalysis, various kind of reanalysis for a predefined or a tailor-made domain. And this might be the vehicle to show the results of this kind of aggregation. We are discussing the future of the Atlas. In the afternoon, we will give you a demo, and Jose Manuel will give you a short introduction to the demo to see what Atlas can bring. So this is just how this kind of results can be shown through this Atlas, which we have developed and we are going to develop in the future and enhance. So that's more how to see this kind of results, not that what is the method to make the aggregation itself. So maybe Hans can contribute to that.
Sure. Hans, do you want to add to that?
Well, basically, you asked the question, when I go to the supermarket and I see 5 different brands of oat milk, which one should I choose? That's what your question boils down. So we give guidance to users, but about which data sets are available best, which are suitable best for what users. But I do agree it would maybe be good if we would try to, to make it easier for the users for them to make the choice of the data set what is best for them, because the word best all depends on what the user requirements are, That's why you have 5 different brands of oat milks, because each individual has his own personal preferences and choices to make that particular choice.
Alison, do you want to add to that?
Yeah, that was a great question. Thank you for bringing that up. So I've only just started working really with the user requirements, and being aware of the things that users want is like the first thing that we need to look at. So I think, yeah, if we can note that and work with users to hopefully implement some of those creating those data sets, I think that would be really valuable. Thanks.
Happy, Peter? Yeah? Okay, he's nodding. So we have another question here.
So a provocative question, will be ERA 6, the last reanalysis built with a global circulation model?
Hans, do you want to comment on that?
Well, we don't know. So because this is such a fast-moving area that we don't know. We don't have. So basically, these kind of things there could be based on best estimates, or gut feelings. But everything is going so fast that even a gut feeling is difficult. So yeah, I don't think that anybody knows the answer. But we're going towards more and more machine learning and artificial intelligence. So now the reanalysis is being heavily used as a training data set for data-driven numerical weather prediction models. But there are also people, and at ECMWF we work on that as well, to go directly from observations to observations. So you don't even need this model anymore. And then the future reanalysis could be ERA 7, could be ERA 8. We still have a reanalysis because we need to reanalyze not only for machine learning, but machine learning has something applications, a new kid on the block that came along a few years ago. But before that, of course, we had already, we had hundreds of thousands of users that are not machine learning. So reanalysis in itself is really important. that might be based on a machine learning algorithm. And one aspect we will particularly think about is that, so we provide this uncertainty estimate for ERA 5 and ERA 6, and that is relatively very costly. So the bulk of the cost is basically in the error estimate. So if we particularly can exploit the machine learning technologies that we will develop for that error estimate, and that means that we can produce it much cheaper, and therefore we can use the total sum, the envelope of the resources that we have, to go to an even higher resolution and better best estimate product available.
Thanks, Hans. Do you want to add to that, Andras, on machine learning in the context of regional reanalysis?
No, because I agree with Hans that whatever we think today, it might be obsolete tomorrow. So I would love to say that there will be ERA 7, but that's only my personal view, and maybe.
Yeah.
And maybe I can add something on
Sure.
the machine learning aspect for ERA 7, for the land atmosphere coupling. I mentioned the machine learning observation operators, but we are also interesting machine learning approaches to develop an ensemble-based land surface data simulation, which makes it cheaper, as Hans said, and yeah, much more suitable. So we developed an emulator of the land surface model from which we can compute our data simulation Jacobians, for example, but also to have a better estimate of the uncertainties at the surface.
If I can just chip in, I think it's worth mentioning that the real gains that we've had so far from machine learning in numerical weather prediction, the real tangible significant gains which are undeniable, have really come from training relative to ERA 5, and that applies across the board. So there are speculative applications of machine learning where you do different things. You go from observation space to observation space. That may deliver in the medium term, but at the minute, the big gains that are on the table are based in reanalysis training. So I just think that's worth reminding ourselves. Okay, there's one question there that I'd really like to put to Leif, because I thought his talk and the economic benefits of ERA 5 was potentially really, really important for the future, for us to justify that component of the service. And it is, when you look across the spectrum of applications and the economic value, is there a dominant sector in application that really stands out as driving that economic value? And from a physical science perspective, if you're trying to establish an uncertainty on a measured or estimated parameter, one of the first things you do is you look at the dominant aspect of that measurement problem and you get that right. So the quote there is, and it's mine, it's better to be roughly right than precisely wrong. So in that context, how does that analogy translate into this economic value analysis, in which you'd guess at the dominant area, domain that's driving economic value?
So, okay, there's a lot to unpack there. I think on the last part of it, is it directly transferable, you know, this notion of certainty in the estimations we're making when you think of, you know, what this community is about? I would say no. So, you know, when you do this type of economic value, especially the economic part, obviously, analysis, you want something that is, of course, well defensible, but it doesn't go to the level of, you know, scientific accuracy or uncertainty. In the first part about which application is the one that is more dominant, I think it's actually AI and ML, and we haven't really been able or had enough resource perhaps to go even further than that. But what's important to state here is that, you know, many entities are training their data sets to do, for instance, you know, AI ML supported numerical weather prediction. But they may also use the same things for something completely different afterwards, which may generate lots of money for them. And you can trace it back to the fact that they had a really great data set to train their models on. So, and this could have a completely different, you know, magnitude of benefit generated from that. So if I had to really choose one, I would say this is the one.
Okay, that's good to know. Any comments in that response? The importance of ML as an application area for reanalysis? I don't see any hands at the minute. So we've got a few more minutes. Carlo's going to comment.
Yeah, I guess it's more of a comment rather than a question, but it is partly addressing the point that was raised by Hill. And we don't know whether we will be able to have a machine learning-based reanalysis, but we do know that when machine learning-based forecast came about, ECMWF and people working around ECMWF and C3S were incredibly quick in understanding the potential of it and investing on it. So the fact that AIFS is now semi-operational and the output are available, so that's the machine learning-based prediction that is available, I think is a demonstration of the fact that we can make the transition. So should there be any evidence, and we are actively looking for it, for machine learning to become available also for reanalysis, hopefully we'll be equally able to make that transition rapidly.
Yeah, thanks, Carlo. I think we've got time for one more question, and I'd really like to tackle this. This question that was aimed at Delphine. Alison's replaced Delphine in Hans. And it is really, we always say the service is user-driven. The users define the requirements and provide the justification for the service. So in the context of reanalysis, given the huge explosive growth in the user numbers and the diversity of that user base and application areas, are we confident that we've sampled that landscape efficiently to drive our specifications for next generation reanalysis? Is there aspects of what we've done so far that have gone well? What could we do better in future? Maybe Hans and Alison?
Okay. Well, so there's a massive amount of literature about ERA 5. So if you look at the number of people that refer to the ERA 5 data in scientific publications, is really immense, also for ERA interim. So one way what we there's already a lot of knowledge. There's tens of thousands, literally tens of thousands of scientific papers written about ERA 5 that anyway use ERA 5 can be like we use ERA 5 because we like it, this helps us out this application, but they also write about ERA 5 doesn't do a good job in that and that and that situation. So we have to learn from that. So what we want to do more is to really dive more into that existing literature, so that we can already harvest everything that is already available, rather than trying just to ignore that and try to do everything ourselves.
Yeah, I absolutely agree. You mentioned there were 14,000 papers or something referencing ERA 5, so I think being able to delve into those and somehow pull out information about what accuracy people need or how they're using the data sets really important. But we also have open forums that people can go onto and ask questions, and as I've started monitoring that forum, I do take note of things that do come up often. So I think we need the users to be quite active in engaging with us from that point of view. And yeah, we're working with a consortium in Germany called CSOC, so we're working with academics there who look at a broad variety of phenomena from ERA 5. So I do think we are doing quite a good job of sampling those user requirements, but we do, the more feedback we can get, the better.
Thanks very much. Leif?
Yeah, if I may, just a very quick comment on this, perhaps stepping a little bit outside of my boundaries, but I think there is also a semi-hidden feedback loop. Because when we, for instance, conduct this type of value chain analysis that we do in this study, of course, the first entry point is someone who really uses ERA 5. And they give you the feedback on limitations, on expectations, on what works well, what not. But then there is someone else further down the value chain who uses what this first entity produces. And actually, they are the, in a sense, real user of the output that is informed by ERA 5. And if you can also capture their expectations and their needs, their operational workflow requirements, and so on, that's probably going to make you wiser. I'm sure you're already doing it, but I felt it's important to highlight.
Thanks very much. That's a really... Okay, Anke, we're really well over, so a quick, punchy question we can take.
To supplement what Alison said and ask a question for later, should the EQC contract and the EQC approach to reanalysis take care of this literature review and synthesizing what has been published in the literature?
Hans, do you want to comment on that? EQC, capturing requirements, is that the natural vehicle for it?
So for very short, yes, I think that's, maybe Shinji, you want to, yeah. You can maybe give the microphone.
If you just wait for the mic.
Thank you bring up Anka, because I'm just listening your comments. Actually, several questions, even the comparison of regional reanalysis with ERA 5. I think that's also one point we would like to address in the EQC contract as well. And also the user. Now I know that you're also doing the user requirement. That's what we are already doing. That we really contact the real users to see what they are going to do with the data set, and in terms of the quality, what the questions they would have. So we will address that questions. Yes, that's definitely the reference, the literature review. That's also one point we will address as well, because we're not able to do everything. I mean, it's how to say, ERA 5, we see so many use cases and citations, so we will try to do also the literature review as well.
Thank you very much. It's a good point. Okay, we really are really long over, so it just remains to thank the speakers once more and start again at 2 p.m.